Hi, I'm Dixon Tsai, and this is the second installment of Data Structures in 5 minutes. Today I'll be talking about graphs, because graphs will give us a more intuitive understanding of data structures that we'll discuss later, such as trees. In mathematics, a graph is represented as a collection of two sets, a set of vertices and a set of edges. So, observing this graph, which is an undirected graph because there are no directions related to the edges, the set of vertices contains vertex A, vertex B, and vertex C, and the set of edges contains edge A, B, B, C, and AC. And these edges are, the pairs are unordered, so you can easily say BA, CA, and CB. We turn our attention to directed graphs now. Directed graphs are different in that each edge is associated with a direction. And so you have the vertex set being the same, C, D, E, F. However, the edges are ordered pairs. So you have CE, EF, ED, FD, DC, but not DE because there's no specific edge and arrow pointing from the origin D to the destination E. Some more terminology here. Two vertices are adjacent if there's an edge connecting those two, and an edge is incident to a vertex if the vertex is one of the two vertices that the edge connects. So we can be able to talk about stuff like a degree, where the degree is the number of edges incident to a certain vertex. So the degree of A is 2, the degree of B is also 2, and the degree of C is 2. In directed graphs, we talk about in degrees and out degrees. So for E, which is the origin, there are 2 edges coming out of it, so the out degree of E is 2. And for F, there's 1 edge coming into the destination here, so the in degree of F is 1. All right? And now we can talk about other terminology here. So a path is a sequence of vertices between vertex 1 and vertex 2, which are the vertices connected by paths. So CED is a path connecting vertex C and vertex D. Now, if you wanted to calculate the length of a path, you would name the first vertex 0, and the last vertex L minus 1. So this is 0.0, 0.1, and 0.2, so D is 2 and L minus 1. That means L is 3 and the length of the path is 3. So a cycle is a path that begins and ends at the same point, so you can easily extend the path we were talking about to a cycle. So CED to CEDC. And there's also another cycle here, CEFDC. Now, a simple path is a path with no repeating vertices. So all the paths we've been talking about so far are also simple paths because there's no one vertex that repeats. And so a simple cycle is a simple path plus the original point. And so you have CEFDC being a simple cycle. Finally, the notion of connectedness is very important in graphs. A graph is connected if there's a path between every single pair of vertices. And so you have AB and AC being connected, and so, yeah, it's a connected graph. For a directed graph, you have the term strongly connected because the conditions are much more stringent. And so that's that. And finally, a graph is complete if there's an edge connecting every pair of vertices, not just a path. So this first graph happens to be a complete graph. Now let's talk about how to represent these graphs. So first, you have an adjacency list, which lists all the origins and their corresponding destinations for directed graphs. For undirected graphs, you'd list both. So for undirected graphs, you'd list C here, but since this is a directed graph, there are specific directions. And the other option is the adjacency matrix, where you have the origins here, the destinations up there, and a true if an edge exists between them. You can see that adjacency lists are good for emptier graphs, and matrices are good for more complete graphs. I'll leave it up to you to see why. And finally, let's talk about 2 algorithms really quickly. These are traversal algorithms. First one is step first search, where you want to search as deeply as you can before you move on to your next option, while breadth first search emphasizes that you want to explore each distance equally before you continue on. So let's say you started at point A, then you would search very deeply here, A, C, E, G. And then you go back to the place where you had another option. E could go to B too. So you explore B, and then finally you have DFH. If you start at point G, you can see that you can go very deeply here. G, E, C, A, D, F, H. And finally, since there is an option here, you could visit B. For breadth first search, it's completely different. You want to go a distance of 1 first. So you have C, B, D if you start from A. And from C, you go to a distance 2, E. But E's already visited, so it doesn't matter for B. D's next one is F of a distance 2 away from A. Finally, you have GH. And I'll leave the last one to you as an exercise. And one last observation, side effect. For breadth first search, gives you the shortest path between the start vertex and every other vertex after that. And you'll also see why. So I condensed a lot of information into these 6 minutes. So sorry for going over, but this is very important stuff, and we'll be building upon these concepts next time.